The atmosphere around us is in constant motion. Huge masses of air sweep across continents. At any moment in time, approximately 2,000 thunderstorms rage on the surface of the Earth. And across the globe, the development of other types of storms, such as hurricanes and blizzards, pose a continual threat to life and property. What powers the motion of the Earth's atmosphere, and what unique combination of variables have to come together to create severe weather conditions such as thunderstorms, tornadoes, and hurricanes? A number of forces work together to create the motion of the air in the Earth's atmosphere. The heat energy of the sun, the Earth's annual orbit around the sun, the rotation of the Earth on its axis, and the uneven absorption and reflection of solar energy by different Earth surfaces. The orbit of the Earth around the sun, combined with the constant 23.5-degree tilt of the Earth on its axis, leads to the generalized weather patterns we call seasons. In the northern hemisphere during the summer, the sun's rays are centered north of the equator, which creates longer days in the hemisphere, along with a shorter, more direct path through the atmosphere to the Earth's surface for the sun's energy. The combination of these factors means that more solar energy is available to fuel the motion of the northern hemisphere's atmosphere during the summer. During the winter, the Earth's orbit places it on the opposite side of the sun. Since the Earth's tilt remains constant throughout its orbit, the sun's rays are now centered south of the equator. Thus, the solar energy available in the northern hemisphere decreases, and the colder winter weather patterns develop. The rotation of the Earth on its axis creates a daily cycle of day and night that causes an uneven heating of the Earth's surface and atmosphere. The uneven heating of the Earth's atmosphere is further increased by the fact that different parts of the Earth's surface, such as oceans, deserts, and snow-covered mountain peaks, all absorb and dissipate heat at different rates. For example, ocean waters absorb and dissipate heat much more slowly than do desert sands. This is one of the reasons that day and night temperatures in coastal cities like San Francisco and Seattle typically vary only 10 to 15 degrees, while temperature variations of 20 to 30 degrees between day and night are common in desert cities like Las Vegas and Phoenix. Clouds also contribute to the uneven heating and cooling of the Earth's surface and atmosphere. The tops of clouds reflect solar energy back into space, while the base of low-lying clouds and phenomena such as fog trap the Earth's stored heat near the surface so that it can't escape back into space. Thus, an area that experiences low cloud cover all day won't become as warm as one that has clear skies. On the other hand, an area with nighttime cloud cover won't cool off as rapidly as an area with no nighttime cloud cover. A lack of cloud cover is another explanation for why the desert often cools so rapidly at night. The uneven heating of Earth's surfaces leads to a flow of air that we refer to as the wind. Winds result as cold, heavy, high-pressure air rushes in to displace warmer, lighter, low-pressure air. Wind farms on Altamont Pass, south of Oakland, California, are able to generate electricity due to the strong winds created by the flow of air between San Francisco Bay and the San Joaquin Valley. During the day, cold, high-pressure air from the bay rushes through the pass to displace the warmer, low-pressure air in the valley. At night, the wind blows in the opposite direction, as air in the valley cools rapidly to become heavier than the air over the bay. The rotation of the Earth not only creates a flow of wind through the uneven heating of the Earth caused by the cycle of day and night, but through what is known as the Coriolis effect, which causes a subtle counterclockwise motion in flows of air in the northern hemisphere and a clockwise motion in the southern hemisphere. The circular flow of air produced by the Coriolis effect is referred to by meteorologists as cyclic flow. The cyclic flow of air created by the Coriolis effect becomes intensified as winds rapidly rotate around areas of extremely low pressure in destructive weather phenomena such as tornadoes and hurricanes, which we will look at later. Air not only moves horizontally along the surface, it also moves vertically. The vertical movement of air, like cyclic flow, is, as we will see later, also crucial to the formation of severe weather phenomena. The formation of cumulus clouds on a warm summer day provides a visible example of the vertical movement of air. As warm, moist air rises from the surface, it begins to cool and condense as it reaches higher altitudes. The base of cumulus clouds form where water vapor first begins to condense into water droplets. The stronger the vertical movement of air in the atmosphere, the higher the cumulus cloud will rise. If it is strong enough, it will rise high enough to form a cumulonimbus or thundercloud. The type of weather phenomena that occur in a region usually varies with the season. In North America, much of the most violent and spectacular weather occurs during late spring, summer, and early fall, when solar energy is at its peak in the hemisphere. Solar energy can be thought of as the engine that powers all atmospheric motion, and it is at its most powerful during the summer in the northern hemisphere. All severe summer weather is usually associated with heavy rain, lightning, and high winds. But there are substantial differences between major summer weather phenomena, such as thunderstorms, tornadoes, and hurricanes, in terms of their size, strength, duration, how long they take to form, and where and when they occur. Thunderstorms, which are common throughout much of the United States during the summer months, are usually more the result of localized weather conditions than of large continental weather patterns. Thunderstorms usually occur during the afternoon, as they require a tremendous amount of heat energy to power the strong vertical flow of moist air necessary to create them. As we saw earlier, it is often possible on a humid summer afternoon to watch as vertical surges of warm, moist air slowly build thunderheads that rise thousands of feet above the earth. The hotter the day and the more moist the air, the higher the thundercloud builds. As the warm, humid air rises, it cools off and condenses, forming precipitation which eventually becomes too heavy for the vertical surges of air to support. This initiates downdrafts within the thundercloud, which are further intensified by the influx of cool, dry air from above. Tremendous turbulence is created within thunderclouds by the violent interplay of updrafts and downdrafts. That turbulence is reflected in the billowing structure of thunderclouds. The anvil top characteristic of thunderclouds indicates that a thundercloud has reached its maximum height, usually about 12 kilometers above the earth, at the base of the level of the atmosphere called the stratosphere. Usually shortly after a thundercloud reaches its maximum height, a powerful downdraft within the thundercloud forces a massive burst of cold air to be released from its base. This is followed almost immediately by the release of precipitation from the thunderhead in the form of rain or hail, gusty winds, and lightning. Once a thunderstorm begins releasing precipitation, it slowly begins to dissipate and lose strength. But it may take hours to use up the huge amounts of energy stored in the typical thundercloud. Thunderstorms can cause death and destruction in a number of ways: flash flooding, hail, and lightning. When a huge amount of precipitation stored in thunderclouds is suddenly released, flash floods can result. Flash floods can be a particular danger to motorists, as cars are often swept off low-lying stretches of roadway by raging torrents. Individuals who find themselves next to streams or rivers flowing through a narrow canyon during a flash flood can find themselves suddenly confronted with a wall of water and with very few escape routes. The moisture stored in thunderheads occasionally comes down in the form of hail. Hail is formed in thunderclouds with abundant supercooled water. Hailstones can range from pea-sized to larger than a baseball. Larger hailstones tend to be formed in particularly turbulent thunderheads, growing bigger and bigger as they are carried up and down in the supercooled precipitation of the thundercloud by wildly alternating updrafts and downdrafts. Storms with larger hailstones can be particularly devastating to farmers who can only stand by and watch as field after field of crops is shredded by hailstones. Automobile dealers can find themselves with an entire lot of cars and trucks with severe body damage after a major hailstorm. Lightning, which accompanies nearly all thunderstorms, is a constant threat to life and property. Approximately 400 people per year worldwide are killed by lightning, while thousands of forest and structural fires are started by lightning strikes, and expensive electronic equipment is often ruined by the power surges caused by lightning striking power lines. The turbulent up and down motion of molecules within thunderclouds appears to build up static electrical charges within a cloud, much as it increases the size of water droplets and hailstones. The huge electrical charges that build up in thunderclouds are either discharged to Earth or to another thundercloud with an opposite electrical charge. The tremendous heat of a lightning bolt, estimated at nearly 28,000 degrees centigrade, causes the adjacent air to expand explosively and creates the sound of thunder. A weather phenomenon just as unpredictable as lightning and even more potentially deadly and destructive is the tornado. Tornadoes are nowhere on Earth more common than along the Mississippi Valley and on the Great Plains of the United States. Two major geographic features, the Rocky Mountains and the Gulf of Mexico, help explain the prevalence of tornadoes in the central U.S. During the spring and early summer of each year, warm, moist air from the Gulf flows up into the central U.S., while cool, dry air from the Rockies also blows into the region. As the cold, dry air arrives, it forces the warm, moist air up into the vertical flow necessary to create thunderstorms. However, these thunderstorms, as they are associated with huge masses of warm and cold air, can extend along lines called squall lines for hundreds of miles. The ominous dark clouds of the squall line indicate conditions are ripe for the formation of a tornado. If anywhere along one of these turbulent lines an intense low-pressure area forms, the result will likely be a tornado. Surrounding air begins a rapid cyclical flow around the low-pressure area. The whirling intensifies to a point where a partial vacuum is created by the winds, rotating at speeds up to 800 kilometers per hour. As surrounding moist air is sucked into the whirling vortex, it condenses rapidly into water vapor, forming a pale white funnel below the dark thunderclouds. If the funnel touches ground, it becomes black as it fills with dirt and debris. As the center of the tornado passes, sealed buildings explode due to the dramatic change in pressure, while others are blown down by the 800 kilometer per hour winds. As the 150 to 600 meter vortex of the typical tornado travels along the ground at 40 to 65 kilometers per hour, its winds travel an unpredictable path of destruction. Over 100 people are killed and millions of dollars of damage are done during a typical tornado season. Fortunately, the life of a tornado is typically limited to less than an hour, as the rapid intake of surface air fills in the low-pressure area aloft and causes the tornado to lose energy and eventually die out. Hurricanes and other tropical cyclones, unlike tornadoes, typically last 5 to 10 days and have been known to last for 2 or 3 weeks and can take days or even weeks to develop. Like tornadoes, hurricanes and other tropical cyclones tend to form only in certain geographical areas and under specific atmospheric conditions. Hurricanes, which are the tropical cyclones that affect North America, start over open tropical waters near the equator between the months of July and November, when the heat energy in the area is at its maximum. As warm, very moist air over these tropical waters begins to rise, the water vapor begins to condense. This condensation releases more latent heat energy, which further powers the upward flow of air. If a low pressure center exists in the area, the upward flowing air forms a counterclockwise cyclic flow around the low pressure. The low pressure area forms the eye of the hurricane, which is usually about 20 miles in diameter, with little wind and clear skies. Surrounding the eye are the wall clouds, which produce the highest winds and heaviest rains associated with the hurricane. The overall diameter of the typical hurricane is between 200 and 300 miles. At first, developing hurricanes travel slowly to the northwest, picking up speed as they reach the mid-latitudes. As a typical hurricane moves north along the coasts of Florida, Georgia, and South Carolina, it usually begins to be pushed to the northeast by prevailing westerlies that usually force the hurricane back to open ocean by the time it reaches the Cape Hatteras area of North Carolina. By the time a hurricane reaches North Carolina, the ocean water is much cooler, which results in the hurricane having less energy with which to power itself. The typical hurricane usually blows itself out somewhere in the middle of the North Atlantic Ocean. However, occasionally, the prevailing westerlies fail to force hurricanes back out to sea, and they continue inland. Typically, hurricanes tend to die out rather rapidly as they start across land, as frictional resistance to the hurricane winds increases and the storm loses its energy source, warm, moist ocean air. One exception to this rule was Hurricane Camille, which in 1969 hit land on the Gulf Coast of Louisiana and then drew an eastward arc across the U.S. to the Virginia coast. To be considered a full-fledged hurricane, the winds of the storm must be at least 74 miles per hour. The winds of hurricanes can reach in excess of 150 miles per hour. Making matters worse for individuals in the path of a hurricane is the fact that tornado funnels can develop within hurricanes, producing a double deadly threat. The lengthy development time of hurricanes and the advent of weather satellites mean that generalized warnings can usually be sounded days in advance of the arrival of a hurricane. However, with average energy levels estimated to be equivalent to 500,000 20-kiloton atomic bombs, the size of the bomb dropped on Nagasaki, Japan, advanced warning isn't always enough. One recent hurricane that struck the U.S., Hurricane Andrew, killed 54 people and caused $22 billion in damage to the Bahamas, Florida, and Louisiana in spite of advanced warnings. Hurricanes do their damage through violent winds, explosive pressure changes, and the flooding caused by torrential rains that can exceed 36 inches in a 24-hour period, and the massive increase in coastal waves caused by high winds. The majority of the atmosphere usually isn't whirling rapidly around an area of extremely low pressure, as is the case with tornadoes and hurricanes, but rather moving slowly in huge blocks of air called air masses. Air masses are often hundreds or thousands of miles in diameter and extend miles up into the atmosphere. The continental United States can be entirely covered by only 2 or 3 air masses. Within an air mass, the temperature, humidity, and pressure of the air is relatively constant, and as a result, winds in the air mass are relatively light. The type of air found within an air mass depends on where it originates. Air masses that originate over water tend to have a lot of stored moisture, while those that originate over land tend to be dry. Likewise, air masses formed over polar regions are made up of cold air, while those forming over desert and tropical areas are warm. Air masses are formed as air remains parked in areas of little or no wind for days or even weeks. The weather in the continental United States is affected by 4 different types of air masses, originating in a number of different areas. Cold, moist air masses originating in the North Atlantic and the North Pacific, cold, dry air masses from central and northern Canada, warm, moist air from the Gulf of Mexico, Caribbean, and Middle Atlantic, and warm, dry air that forms over the deserts of the southwestern United States and northern Mexico. The type of weather conditions that exist within an air mass after it leaves its area of origin depends on whether the surface it is traveling across is colder or warmer than the air mass. If the ground or body of water that the air mass is passing over is colder than the air mass, one of 2 phenomena usually occur. As a moist air mass passes over a cold surface, the moisture in the lower levels of the air mass often condense to form dew, fog, drizzle, or light rain. If the air mass is dry, a temperature inversion may occur in which a layer of cold air is trapped beneath the warmer air mass. As a result, smoke, dust, and other pollutants can't rise, and a haze or brown cloud develops. Such temperature inversions are common in Denver, Colorado, and other cities during the winter months. If a moist air mass crosses a surface warmer than the air mass, convection currents start to generate wind, and cumulus clouds are formed as the moist air, warmed by the surface, begins to rise. If the warm surface is a lake or ocean, or if the air mass is very moist, cumulonimbus clouds may develop and generate strong rain showers. A dry air mass crossing a warmer surface usually creates clear and sunny conditions. Along areas called fronts that lie at the boundary between air masses, the formation of clouds and the levels of precipitation, whether rain or snow, are usually much greater than they are within air masses. In fact, on satellite weather maps, the movement of air masses is usually obvious due to the high concentration of clouds found along weather fronts. The movement of a front through an area always creates some sort of change in the weather. A sloping intersection between air masses is always formed along a front, and the cold air mass is always wedged below the warm air mass. There are 2 major types of fronts: cold fronts and warm fronts. Cold fronts and warm fronts differ in a number of ways. Cold fronts are formed when a mass of cold air pushes a warm air mass ahead of it. As a cold front passes an area, winds increase and temperatures drop rapidly. Cold fronts have a steeper slope than warm fronts, as the higher level air in cold masses moves faster than the lower level air. As a result of the steep slope, the air in the warm air mass is forced up rapidly, and as it rises, it forms cumulus and cumulonimbus clouds. These cumulonimbus clouds often produce a short, heavy burst of rain showers. If a warm air mass is very humid, a squall line can develop along the cold front. Squall lines can sometimes stretch for hundreds of miles. Because of the steep slope that creates them, the line of clouds that form along a cold front usually only extend 150 to 250 kilometers on either side of the leading edge of the front. Thus, cold fronts can usually be identified on satellite photographs by the much narrower band of clouds along their fronts as compared to the system of clouds associated with warm fronts that can extend for up to 1,500 kilometers ahead of a warm front. Warm fronts are formed as a warm air mass pushes a cold air mass ahead of it. A predictable series of clouds form along a warm front. Very high cirrus clouds, made up of ice crystals that form thin white patches or strands in the atmosphere, lead the way. Slightly heavier cirrostratus clouds that appear to create a haze or a halo around the light from the sun or the moon follow right behind the cirrus clouds. Both of these types of clouds are found at least 6,000 meters above the surface. Following behind these clouds at a height between 2,000 and 6,000 meters above the Earth are bluish-gray fibrous clouds called altostratus clouds, through which the blurred light of the sun or the moon are barely visible. Trailing the altostratus clouds at a level of 2,000 meters or less above the surface are heavier layers of stratus and nimbostratus clouds that may entirely block out the sun. Stratus clouds are often associated with light scattered drizzle or snow, while thicker nimbostratus clouds usually produce steady rain or heavy snow. The region of rain or snow produced by the stratus and nimbostratus clouds usually extend for hundreds of kilometers beyond the leading edge of the front. After a warm front passes, a period of warmer, more stable weather usually begins in the region. All weather phenomena, from hurricanes and tornadoes to coastal fog and afternoon thunderstorms, result from the flow of air through the atmosphere. A number of forces work together to create the motion of air in the Earth's atmosphere. The heat energy of the sun is the power source behind the motion of the atmosphere. An uneven distribution of solar energy throughout Earth's atmosphere results from variations in the rates at which different surfaces, such as ocean waters and desert sands, absorb and reflect the sun's energy. A flow of air, which we refer to as the wind, is created as cold, heavy, high-pressure air moves to displace warmer, lighter, low-pressure air. The rotation of the Earth on its axis creates what's referred to as the Coriolis effect that causes flows of air in the northern hemisphere to rotate counterclockwise and flows in the southern hemisphere to rotate clockwise. This rotation takes on its most extreme form in tornadoes and hurricanes. Different types of clouds are created as the warm, moist air is carried to higher altitudes and condenses. The types of clouds that are formed at these higher altitudes can help provide an indication of what kind of weather is in store for a region. A thorough understanding of the forces that control the motion of the atmosphere, from huge continental air masses to highly localized phenomena such as thunderstorms and tornadoes, is critical for meteorologists and other scientists attempting to better predict and perhaps one day modify and change weather patterns.